Okay, so today we will talk about PCA, which is Principal Components Analysis. And the idea here is it can be seen as a method of dimension reduction, okay? Can be seen as a dimension reduction method. One way to think of it also is what PCA tries to do is it tries to basically pick out structure in the data. Yeah, I guess so. A way to identify structure in the data. Okay, there's so some might consider this to be unsupervised learning. I guess that's fine, but yeah, basically we use PCA to try to identify structure in the data, and there's this idea of projection. Okay, projection is the idea of projecting high-dimensional data onto something that is of a lower dimension, okay? Projection is projecting higher dimensional data onto, a lower dimensional space. All right. The most familiar example of this is the idea of our bodies casting our three-dimensional things, casting a two-dimensional shadow onto a wall. Okay, so we have this. It's 3D objects cast a 2D shadow on the wall. Okay, and when you cast something, a three-dimensional object onto something of a higher dimension onto a lower dimension, you're going to lose some aspects. Okay, you don't get to see the whole thing, but you can project things into the two-dimensional space or lower dimensional space in a way that preserves the structure of the data. Okay, so for example, we could have a three-dimensional hand. This is my beautiful art, and if I project it this way with the light coming this way, then the shadow that gets cast onto the ground, this looks very much like a hand. Okay, this shadow looks like a hand. But if the hand was held this way, this is my terrible drawing skills. Okay, we could project just something lumpy that looks like this, right? This is another entirely possible shadow. Okay, and this shadow, while entirely a true projection of the data does not really represent, doesn't look like a hand, okay? This shadow does not look like a hand, okay? Okay, but it's important to note, but is still a projection of the data. Okay, it's just, or projection of the object, right? So we have a high dimensional object, and depending on how the light shines on it and how you are choosing to project the object, you know, what you get to see in lower dimensions may or may not resemble the original data, right? So you know, there's a question like what is important in the hand, or you know, in the object that we're trying to represent. And we would probably say that, oh, okay, you know, if you see this shadow on the wall, you would know that that's a hand, right? If you see this shadow on the wall, you probably would not. Or I mean, you might, but less so, right? And so PCA is the idea of, okay, we want to project our high dimensional data onto something of lower dimensions, and we want to be able to preserve the structure, or we want to preserve the interesting features. We want this shadow, we don't want this, right? That's basically what we are going for. We want this, not this. Okay, and so one way to think of this is we want to create a projection that will maximize the variance in after we project the data. Okay, so that maximizes the variance, you know, after projection. So, so for example, let's say you have this is, so here's two-dimensional data. And the idea here is, let's say we were going to project this onto just a one-dimensional surface, right? So we have 2D data, okay? We will project to one dimension. And so, you know, one option is I can shine the light over here. And if I shine the light over here onto, let's say, let's see, I probably want this, and if I shine the data onto this surface, let's see, then everything, our data we would get a histogram that looks with dots that look kind of like this. And if I were to build a histogram, it would probably look something like that. I don't know. Okay. Whereas if I projected the data from another direction, okay, and the light is shining this way, the resulting data would get projected down onto here and onto here, and my resulting histogram, would look something like that. Okay. And which of these or densities has more variance? And the one that has the obviously the bimodal one will have more variance, right? Because variance is, what's the kind of average distance from the mean, and clearly this one, most of the data, there's hardly any data that's right at the mean being kind of in the middle. There's very few points that have small distances from the mean. Almost all the data has, moderate to high distance from the mean. And so this one will have more variation. Okay, so this density has more variation. Okay, so none of the points, none of the observations are very close to the mean. Okay, and if we project it this way, we would preserve kind of the cluster nature, the clustering structure in the data, whereas projecting it this way, we would not see that there are two distinct groups. Okay, so this projection preserves the two distinct groups in the data. Okay. The other projection does not preserve that structure. Okay, and so we want to basically, so a principal component is going to be a linear combination of the original data. So we've got kind of you've got your different dimensions in the original data, and they're linear combinations of the original data in such a way that that will maximize the resulting variation. So let's so we'll start with our okay, so we will project m dimensions down to d dimensions. Okay, and so all right, and so we will so PCA will define d vectors. Okay, which will be WD, this vector, and each vector is m dimensional. Okay, because this WD is kind of the recipe for how to combine the m original variables. Okay. Combine the original and variables. Okay, so if we're taking 10 dimensions and we're going to project it down to 2 dimensions, we will end up with 2 W vectors, and each W vector is how we should combine the original 10. And it might say like, okay, you need to weight, the first variable, at 40%, and the second variable at 5%, and the third variable at, at these different percentages or different amounts, and we'll end up having 2 of these things. Okay. All right, and then so the resulting data, the resulting projected data, X will be d-dimensional, and you'll have and so you'll have X and D will be the dth W transpose times kind of your y vector, the nth y vector. Okay, so let me just kind of say this. So let's say y is in 10 dimensions. Okay, so we'll say y sub 30 is the 30th observation in 10 dimensions. Okay. W sub 1 is the kind of the first, quote, loadings. It is 10-dimensional. It is 10-dimensional, and so W1 times yn, how many, not yn, we'll say y30, what is the dimension of this thing that results? It's just a single value, right? This is going to be just a single value. A single value, okay? So y sub 30 is the 30th observation in your original data. There's 10 elements in it because it's 10-dimensional data. And then you multiply it by W1, and W1 is kind of how much of each of those original 10 things, how they're weighted together, okay? We multiply it by that, and we get a single value, right? And then if we do this for W2, we will also get, so this will be x1 30, and then we will get x2 30, okay? And then so now we have x1 30 and x2 30. This is these two values make our two-dimensional representation of y30, which was originally had to be represented with 10 different numbers, right? So just like we could create a model of my hand, right? And every location on this hand would have 3 coordinates, but then after we project it down to a shadow, that resulting thing only has 2 coordinates, okay? So likewise, each data point in y has 10 coordinates, okay? This is our 30th data point in y, has 10 coordinates. After multiplying it by our principal components, each data point is now represented with only 2 coordinates, okay? Or however many things that we have. So this is a case where we're going from 10 dimensions down to 2 dimensions or something like that. All right, is it clear what we're trying to accomplish here? Okay, so just to kind of illustrate a little bit of the math, we're going to go from something even simpler. We're going to go from 2 dimensions down to 1 dimension, okay? And then I think this will kind of work here. Okay, so what we'll start with is okay, so then also the W's, so like W1 and W2, they're all orthogonal. So all the different, like, after you make like 2-dimensional things or, you know, project it down, are all orthogonal to each other. That is, that if you take any 2 W's and you multiply them against each other, you're going to get 0, okay? For all I not equal to j. Okay, and then another thing is that all of the data we have centered the data too. Okay, so we have centered our data, and so that means basically the mean of each variable in the original data is 0. Okay, so the mean of each variable in the original data is 0, or in other words, we would say y bar is 0 for okay. So we'll assume that, okay. And then, okay. So then, all right, so we'll start, okay, so just to do our math, we will use the example of projecting to one dimension. Okay, so in this case, after we do xn times our one and only w vector times yn, so this will just be a single scalar value. And this is our, our one and only w vector. Okay, and what we want to do is we want to maximize our variance. Of the resulting projected data, and so our variance will be x minus x bar squared summed up 1 over n. Okay, and so let me take this. So we want to maximize this. And we know that we know that y bar is equal to 0. So because we said we're starting off with centered data, so that means so x bar is going to be if we look at this, is going to be 1 over n times the sum of w times yn, okay, for each of these things, and this will become w transpose times 1 over n sum of the yns. This becomes y bar, which is 0. So we have w transpose times 0. So we know that so x bar is going to equal 0. Okay, so that makes our life a little bit easier. And so this, so plugging that into there, we now have sigma squared of x being 1 over n of xn squared. Okay, and then so if I plug in what xn was, so keep in mind that x of n is equal to w transpose yn. We now have, continuing this on, we have the sum of w transpose yn squared. I should add little vector symbols here. Okay, and so this, complicating this out, or just multiplying this out, we get w transpose yn transpose w. Okay, and so I can actually move this out, w transpose, and I get 1 over n times the sum product, sum of each y transpose W. Okay. So this is our sigma squared. Okay. So this, if I just say, okay, this will be, so if we think of what YY transpose is, if each y is 10 dimensionals, and then I've got this kind of 10 by 10 matrix, or 2 by 2 matrix, whatever it might be, however many original dimensions that we have, we've got W, and we're going to just call this some matrix C. Okay, so let the matrix C equal this thing. For all the n's, okay. And if we take a close look at this, if we recall that each y has a mean of 0, then this can actually be further expanded to y minus y bar, okay, times y minus y bar transpose. If I okay, keeping in mind that each y bar is 0. Okay, so we can, if I do this, then I don't know if this looks familiar, but this is the covariance matrix. This is the definition of the covariance matrix. Okay, so what we have is we've got our loadings, W transpose times the covariance times W. Okay, so we want to, we still want to maximize this thing, all right? So how can this be done, right? Well, this can be done via Lagrangian, adding a Lagrangian term, and don't worry about this, but all to say is that it turns out we can do this by using an eigenvector, but I'll just kind of show you the kind of the intermediate steps, so it doesn't seem like this came out of nowhere. Okay, so what we have is we have this where C is the covariance matrix of Y, okay? And then to maximize, we'll use a Lagrangian term, okay? And so we have L equal to W transpose CW minus lambda times W transpose W minus 1. Okay, so we want to find the W that maximizes this, and if we take partials with respect to this, then we would get, and that equal to that, and then now we have and the 2 gets eaten by the lambda, just because the lambda is some arbitrary constant. So lambda over 2 can just be lambda. We'll call this lambda A and lambda B. All right, it doesn't matter. So Okay, and if we take a look at kind of the form of this, right? So basically we have matrix times vector is equal to constant times vector. Then what you have is that the solution to this is that, so we have matrix times vector is equal to constant times vector, and that's kind of the idea of what an eigenvector is, right? So this is an eigenvector of the covariance matrix. Okay, because so if you look up the definition of an eigenvector, it will probably be something like let's look this up. Eigenvector. A, so the matrix A times vector V is equal to lambda times V. So you have matrix A times V is equal to lambda times V. So this is your matrix, eigenvector, the lambda is an eigenvalue times the eigenvector. Okay, so all to say, all of this math is just to show that if we want to project the data down into a dimension that maximizes the resulting variance, we would do an eigenvector. We would find the eigenvector of the covariance matrix, okay? Covariance matrix of the centered data. Okay, so I will write that. Okay, so to maximize the variance of the projected data, okay, we will use the eigenvectors of the covariance matrix of the centered data. Is that okay? Are we familiar enough with eigenvectors? No? How can I simply explain what an eigenvector is? So if you think of matrix multiplication, basically when you have kind of input data, and if you multiply it by a square matrix, so let's say we have a square matrix. So just we'll start off with a 2 by 2 matrix. So imagine you've got a plane, right? And every dot on that plane can be represented with a vector, right? Starting from the origin to that coordinate. Okay, and then when you multiply a vector by a matrix, okay, that matrix will transform where that vector ends up going, okay, or where that point goes. So you've got something here, and then so this is your vector, your two-dimensional vector. And then if you multiply multiply it by a, so if you have a times a vector v, generally you've got some, so the A represents some kind of transformation to this thing. Maybe a rotation, maybe scaling it, something, okay? So perhaps after multiplying it, you get something like this, right? So you have some kind of this 2 by 2 matrix just represents some kind of transformation. Represents, instructions to transform each vector v. Okay, so for example, if you have the identity matrix just says don't transform it, leave it as is, okay? But then if you do something like what this would do is it would flip the resulting kind of, it swaps the x and the y coordinates, okay? So that's another transformation, right? Swap x and y. Okay, so, and basically every single two-dimensional vector, or two-dimensional matrix, 2 by 2 matrix, represents some kind of instructions on combining or combining the x and y coordinates in a way to produce a new vector. Okay. These matrices, however, if you apply them to certain coordinates, like if I apply this swapping instruction, we would get this, right? And if I had this thing, then the resulting vector would be that. And if I had I don't know, this vector, then the resulting vector would be, what would it be? I swap the x with the y. So I think it would end up being like this, okay? And but some vectors, if I apply this transformation to it, will not be affected. So if I do this, the result after the transformation ends up being exactly the same, or perhaps just it has expanded or something like that, okay? So some vectors will not change directions after applying the eigenvector, or after applying the matrix, okay? And so those vectors that are unaffected after multiplying by the matrix, those are considered eigenvectors of the matrix. That multiplying by the matrix basically doesn't change the direction of the original matrix. So pretty much it's like, you're given these instructions on doing something to the coordinates, but those ones remain unaffected, okay? And the ones that remain unaffected are considered eigenvectors. Okay, anyway, let's just try this out on some data here, okay? Okay, so we have some in the handbook textbook, there is data from a heptathlon. Okay, so heptathlon, there are 7 Oh yeah. Sorry. Does that fit? Okay. All right, let's just take a look. Let's do view heptathlon. Okay, so in the heptathlon there are 7 events. We got hurdles, high jump, shot put, 200-meter run, long jump, javelin, and 800-meter run. I think that's 7. 1, 2, 3, 4, 5, 6, 7. Okay, and then based on your performance on each of these things, you get some kind of score, right? And I don't know what the I don't know exactly the Olympics formula for calculating the score is, but basically what they want to do is you want to find a way, how can we combine the performance of these 7 different events in such a way that we can rank our athletes from number 1 to last place, right? So what we have is we want to project from 7 dimensions down to just 1 dimension. Okay, that's effectively what we want to do. So so what we're going to do for a few of these things is we want to we're going to put everything so that higher scores are better. Okay, so we're going to for the time-based ones, which is the running, the hurdles, the 2 running events and the hurdles, which is also a running event. We're going to just reverse those. Okay, so we're going to say the hurdles, we're going to take the maximum and subtract each hurdle score. Okay, so we'll get each of these things, and then I'm just going to extract the score. All right. Okay, so the score. Okay, so is the 8th column. So we're just gonna. So if I plot all of these things without the score, see this? Shoot. Let me see if I can. Okay, so this is our 7 by 7 plots, and we kind of it's a little hard to see, but some of these events we've got some high correlation, right? Like hurdles seems to correlate pretty well with high jump, shot put, the running and the long jump. It doesn't seem to correlate very well with javelin, but maybe correlates well with a lot of these other ones. Yeah, javelin just doesn't seem to correlate very well with many of the other plots. So if we look at javelin versus this, or javelin versus any of the others, not a whole lot of correlation, but the other ones seem to correlate well. But anyway, what we want to do is we want to somehow compress all of these down to 1. Okay, and if we look at all of this, we do see that there is one athlete who, compared to everyone else, just performs a lot poorly. So we may choose to remove that person, maybe not. Okay. What we'll do is we're going to calculate the correlation matrix of our athletes. Okay, let's see. Oh, I didn't. So if I calculate the kind of the correlation matrix, this is what we'll end up having, okay? And if I just take a look at heptathlon here. What did I do? 1, 2, 3, 4, 5, 6, 7. Oh, we removed the outlier. Okay, so so Launa of PNG was our poor performer. Okay, so we removed that. We removed the outlier from our data. Okay, and then if we redo that and we calculate the correlation, we get slightly different numbers here, and we can create the plot here again with our outlier removed, and it looks pretty much, I mean, not the same, but we don't have that kind of that one outlier scrunching up our data anymore. Okay, so yeah, we see hurdles correlates very well with the 200-meter run and the long jump. Okay, and then interestingly enough, shot put also correlates well with high jump and 200-meter run and other things. Again, javelin's still all over the place, but that's what we have. Okay, so how can we do principal components analysis? Well, one way is we can just use the command prcomp. There's also a command pca. Okay, we can do prcomp, and this with scale equals true puts scales all the variables to have a variance of 1, which is a desirable thing. And here it just produces all of our principal components, and it says these are the kind of the loadings that we would use. Maybe that's not all that much. If we multiply the result of our principal components matrix, okay, so this is this first column, PC1, this is the first principal component. This is pretty much the eigenvector, the first eigenvector of our correlation matrix. This will be the loadings here. So what we want to do is we would take these loadings and we would multiply our data, for our contestants are 24, or in this case 23 contestants, and we would multiply them by our 7 loadings here to kind of get maybe the score that we want. Okay, so what we want to do is we can take our the center and the scale, and we will take our heptathlon data. So here is as a matrix just the 7 things, and we're going to scale our data. Scaling our data, what that does is it centers it so everything has a mean of 0, and it scales it so everything has a variance of 1. Okay, and the reason why we want to center and scale our data is that, again, we're trying to maximize the variance, but we want to preserve the structure. And so if we didn't scale the data and one variable was just, let's say we measured, let's say, I don't know, for some silly reason, the Olympics measured, you know, the race times, the 800-meter race times in seconds, but then it decided to measure the 200-meter race in milliseconds. Okay, and so with the 200-meter race, you know, you're getting how long do they run? I don't know. You know, instead of values of 4.05, you're getting values of 4,000. Okay, and if we wanted to preserve, you know, maximize the variance, then it makes sense to just try to, you know, weight the one with the huge values as much as possible. Okay, so if you don't scale the data, the result is that any variable in the original data set that had a large amount of variance will just get weighted too heavily. So, so we want to scale all the data so that everything has a variance of 1. Okay, so anyway, we apply the scaling. So this is our data after we've scaled our data. Okay, it's hardly recognizable now, but it's still 7 columns. And then all we do is we just take our centered and scaled data and multiply it by those loadings. Okay, so whoops. A1, this is how much we should weight each of these 7 variables. Okay, so when I do that and I multiply that, this is the result. So each person, they had 7 scores from their 7 different events. It gets boiled down to just 1. Okay, and this is their scoring. Okay, so if we if I plot this now, another way to get our projected data is we can just, this is the exact same thing. Okay. Oops. So here is the correlation. If I ask, what is the correlation between the Olympic calculated score and the after we project our data down onto one dimension using principal components analysis, we get a correlation of about 0.99, which is about as good as we could hope for. Okay, which means the way the Olympics, they have some formula for combining the scores from the 7 different events, just so everybody gets 1 score for the heptathlon. When we do principal components analysis, we find that our principal components analysis of projecting the 7 scores down onto one dimension lines up almost perfectly with what the Olympics are doing. Score is not one of the variables, right? We did this using the other 7 variables. Okay, and we can just kind of create a plot between the score and what the Olympics are doing, and so. So when we project down, you know, this person, you know, according to our principal components analysis, gets scored a little bit lower than what the Olympics formula does, but pretty much everyone else lines up almost perfectly with how, you know, the Olympics. I don't know what they've done. They have a committee to determine how to weight the scores. But we are just trying to preserve, you know, the most amount of variance in our data, okay, by looking at it this way. All right, a biplot shows how the for the first 2 principal components. So really, we're just looking at the first one, and it says you need to weight, it looks like hurdles and long jump and 200-meter run the heaviest, and then high jump, javelin, and 800-meter run to be weighted less, okay, in terms of how these things get factored in. If this doesn't make sense for the Olympics, it doesn't make sense to have 2 dimensions of ranking, okay, because we only want 1 winner. But if we had a second dimension to preserve the second most amount of variance, then then that's what the biplot shows. It shows kind of the second dimension here. All right, let me just show you a few other examples of kind of principal components analysis. Okay, so yeah, I guess I'll kind of work through this a little bit manually here, and maybe I'll just generate 100 random points for X, and then Y. We'll do 10 times X plus maybe 5 times X, and we'll add some random noise to that also. Maybe we should not have as much. Okay, so this is going to be my original data here. And okay, so our original data exists in 2 dimensions, and we'll try projecting this down to 1 dimension. Okay, now how should we do this? Okay, we want to preserve the most amount of variance after we project the data. So I'll do data will be so our data is in C-bind. So our data is a 2 dimensions, 2 columns, 100 rows. Okay, and so to do this using principal components analysis is I would center our data. Okay, so I can just do centered and scaled data. So I'll call the CS_dat will be the function scale_dat just does this for me. Okay, so CS_dat. So if I do column means of CS centered and scaled data, we get basically 0 for each one. And if I do apply CS data to we want the variance. Oops. We get a variance of 1 for both of those columns. Okay, so column means of okay, so we get columns have a mean of 0, columns have a variance of 1. Okay, and then we'll take the correlation of our centered and scaled data. Okay, this is my correlation matrix. And now all I have to do is find the eigenvectors of my correlation matrix. Okay, these are my eigenvectors, and so this first eigenvector represents the first principal component. Okay, it says I want 0.707 and 0.707 of each of these things. Okay, so I'll do take the first vector, and then so if I take this and I multiply that by my data, okay, this puts everybody on the on a single scale here, okay? And so if I and this basically, all it does is it just projects everybody down to a single value here. And so if I want to recreate the original data, okay, so now I've projected everything down to one dimension. Is there, okay, and then to go back, so now we can just kind of preserve all of this, and if we want to go back to the original form, okay, basically this data has now been reduced to a single dimension, and so hang on a second. To go back to the original form, we take our one-dimensional data and we will multiply it back by our the transpose of our eigenvectors, okay? Okay, so this gives us back what we have. So this is just projected back. And then we would have to add back our column means. So let me just find. So let me do points P, and then we'll do color equals red. Okay. All right, so the black represents the original data, okay? And, oh, maybe, did I not scale this correctly back? I've got to multiply it back by the scale. Sorry. X and Y. Here, let's just plot our scale data. Okay. I think, maybe. So, so this, the black represents our original data, and then the red represents the data after we've projected it down to one dimension. And so the red data points preserve a lot of the structure, but again, because we are going from 2 dimensions to 1 dimension, we do lose some information. We don't differentiate between this point and this point. They get pretty much projected to the same spot on the when we look at the first principal component. Okay, so so that's what happens when you do principal components analysis, is that you project the data down into a lower dimension, but naturally you lose some information. Okay, so again, to do that, what I did was I calculated the centered and scaled data. We can just use the function scale for that. And then we take the correlation of the centered and scaled data, and we and so that returns a square matrix, and we take the eigenvectors of that square matrix. You know, I'm just gonna keep going, and then maybe we'll finish a tiny bit early today. Okay, let's look at another example here. No, it's different, because the regression tries to minimize the squared residuals. Principal components analysis tries to maximize the resulting variance, which is they're different things. So it's not going to be the same. Okay, let me load up this example here. Okay, so here I've got in my directory, I have a picture of Audrey Hepburn from Breakfast at Tiffany's. Okay, and so this image is, what are the properties of this image? It's 634 by 791 pixels. Okay, so it's 634 pixels wide, 791 pixels tall. Okay, so I'm using a library called Imager here, and that's what it says. It's got 634 pixels, 791. 634 by 791. It's 1 frame because it supports like movies or GIFs, and I say GIF, but I don't know. All right, you guys maybe whatever. Okay, and then and 3 channels for red, green, and blue, and this is it's a black and white image, so all 3 channels have the same same value here. Okay, so here I'm just going to reduce it to 791 by 634 matrix. Okay, so we'll do this, and this is, so if we look at the dimensions of the resulting thing, now it's just a single matrix, 791 by 634, and I can use plot as image, and here it gets plotted in R like that. Okay, so what we're going to do is we're going to find the column means. So we want to, so each column here now, right? If we look at the head of this, okay, it gets truncated. But each value here now represents kind of like how bright or how dark the pixel needs to be. Okay, and so so I've got a whole bunch of data, and this is so stored in memory. Thankfully, when you store something as a JPEG, or a stored in memory, just all of those elements for this little image stored is 3.8 megabytes in memory. If we store, if every single pixel, 791 by 634, is a double type floating point, it takes up a lot of memory in space. Okay. What we're going to do is we're going to try principal components analysis on this. Okay, and to do that, first we have to find the column means from each thing, and so I'm going to do column means of this image. Hang on, it says there's a bunch of warnings. Let me just clear out my space here. Okay, so that seems okay. All right, no warnings this time. We'll take the column means there, and then we're going to center this by just subtracting off the means from every pixel here. Okay, and I have to do transpose because when you do a matrix minus a vector, R's default behavior is to apply it down a column. So what I'm doing is I'm transposing it, so the rows become columns, then I subtract those, and then I transpose it back. Okay, so when we do this, and we just want to make sure, did all of the column means after I centered it, are they all equal to 0? It is, and if I were to plot this after I center this, just so you can see kind of what this looks like, you can still see the image, just you'll see these streaks in it because we have subtracted out the column means. Okay, so when you zoom in on this, what we have here is we have these stripes because basically the mean of this column was a high number because I guess there was a lot of black in this column, so we subtract kind of the mean of these things so that the average of the column becomes 0. So you get these stripes here because we've subtracted column means. So because here it's there's what did I say, 600 something columns, and we're subtracting the mean from each column right here. Okay, so those get taken out. So now if we take the mean of each column, the mean is 0. Okay, the 0 being kind of like a grayish color. Okay, and then so we subtract the means from these things, and then now we will take the covariance of this entire matrix. Okay, so again, what are the dimensions of this entire image? It's 791 by 634. I take the covariance of this thing. So my covariance matrix is 634 by 634. This is a covariance matrix of the centered data. And then we will find the eigenvectors of this thing. Okay? So if I ask what are the eigenvectors, okay, there's going to be 634 eigenvectors. Okay? Whenever you take eigenvectors of a square matrix, you're going to have 634 of them, and you're going to have 634 eigenvalues. But, you know, so we've got, 634 eigenvalues and 634 eigenvectors. And what we can do is we can just keep the first 50 principal components, okay? So that corresponds to just the first 50 out of the 634 eigenvectors. Okay, so I'm going to call that PC50. And so if I say, what's the dimensions of this? It's 634 by 50. So we've only kept the first 50 eigenvectors. And so I'm going to multiply this centered matrix, so the striped image, against my 50 principal components. Okay, so if we ask what is the dimensions of our data after we've projected it, it's now 791 by 50. Okay, so our original data had 791 rows of 634 columns. I've projected it down to 791 rows of basically 50 columns. Okay, so I've reduced the amount of kind of information, or the amount of data that has to be stored down to 50 columns rather than 634. Okay, so the original image, 791 rows of 634 columns. Now it's just 791 rows of 50 columns. Okay. This projected data doesn't mean much to us because we want to project it back to the original. Like if I were to plot this, of this thing after I've reduced it down to 50 columns, this would not look like anything that we want. Okay, if I okay, it's 791 rows and 50 columns, and when we look at this looks like nothing meaningful to us. Okay, we need it back in the form of an image, which is going to be 791 rows and 634 columns. We need to go back. So to do that, we've projected it down to 50 columns of data, but now we're going to go from that 50 columns of data back to 634. So we multiply the projected data back by those 50 eigenvectors, the transpose of that, and that will return us back to 791 by 634. Okay, so keep in mind we went from 791 by 634 down to 50, and now we're projecting it back to 634. So no file compression system or image compression system uses this, but if we wanted to, we could devise a compression system where I just send you the 791 by 50 matrix along with the eigenvectors, and then your computer then multiplies them back to produce the 791 by 634. Okay, so rather than sending you the entire 791 by 634, I could send you the 791 by 50 plus the eigenvectors, which are 50 by 634. So it's a lot less data. I'd send you these two matrices, which your computer will multiply back. Okay, so we can do that. We get this back together, and then we will add the column means back to our data, and we plot this, and this is the image after we have reconstructed it. Okay, and it looks pretty good. Like if we compare this to the original image, okay, so this is the original image. Okay, this is, you know, full quality versus we've kind of projected it down to just 50 columns, and we do see some blotchiness and graininess, but you can still definitely tell that who this is, and it's an image, and like you would recognize that this is Audrey Hepburn from Breakfast at Tiffany's. Okay, right there, there's some blotchiness here and whatnot, but I would say we have succeeded in terms of creating. Oh, so here's the I don't know if I can. I don't know if you guys can see the difference. So this is the original, and this is the reconstructed image, after reducing it down to 50 columns. Okay, and So I think that's pretty neat, right? And this is the idea of, just taking our very high dimensional data. In this case, we're treating the image as 791 observations of 634 variables each, okay? Because you can treat, the rectangular image like that. And we've reduced, by principal components analysis, we've reduced that 634 down to 50, and that's what it does. Okay, I want to just kind of show you.
I got a question.
Yes.
So you kind of just like took 50 values from the eigenvector, right? Just grab the first 50 of them.
I'm taking the first 50 eigenvectors. Yeah.
Why, like, does order not matter? Like, how come just taking the first 50 doesn't? Like, what if you took like the second 50 or like?
Yeah. So. Yeah, when we go for the eigenvectors, the first eigenvector is going to be the one that captures the most amount of variation, and the construction of the eigenvectors are in such a way that all the eigenvectors are orthogonal to each other, down to because our original correlation matrix is 634 by 634, and if we want to capture all the information in that 634 by 634 square matrix, we would need to have 634 eigenvectors of 634 values each, okay, to truly capture all of it. And but that last one ends up being, contains the least amount of information. And so yeah, so I've chosen to do the first 50, okay, but and we can kind of play around and see, like, what happens if I did only the first 30 or the first 20 or the first 10. And so I went ahead and I did, where did they go? So when you do only the first principal component, okay, so there's 634 eigenvectors, and if you only use the first one and you use this to recreate your image, okay, so you have one eigenvector, so you project 791 by 634 down to 791 by 1, and then you multiply by the transpose to get back 634. This is what you get, okay? So with one eigenvector, this is the image, okay? With two, this is what you get. So this is so this first eigenvector captures the most amount of variation in the image, okay? And then this is kind of the second, adding a little bit more variation here. And we start to see a little bit more structure. Then we add a third principal component, and here it is with 4, and then 5, and at 6. So we're starting to get just a little bit more form here. And here's with 7 and 8, 9, and 10, okay, and at 10, like, a face-ish thing emerges in the image, okay, and here's with 12, so and 14, so I started incrementing at by 2, okay, and here's with 16 principal components, and now we're starting to see, like, you could probably, like, sometimes you look at little thumbnails online and you can kind of guess what the image is. Like at this point, you can probably kind of guess what these things is, just because this image is so iconic. And here, as we increase the number of principal components being used, we can see the image getting more and more clear. And this is with 120 principal components, and I don't know how many of these things I did. So this is at 150. And at a certain point, the image doesn't seem to really change that much. I'm trying to see on my screen. Okay, I can see tiny improvements if I look very carefully on my screen, but I imagine when it's projected on the screen, you don't see any difference between any of these things, okay? But, you know, you can kind of see as we reduce the number of principal components, the quality of the image does degrade. It's like, but you can kind of see how we can successfully project the data down onto something of fewer dimensions and manage to still preserve what we might consider interesting features of the data. Okay, so this image thing is kind of it's like a fun toy, but it's not really used in real life. Okay, like JPEG is probably the most common image compression format, and that uses wavelets? I don't remember. Okay, it uses something. Okay. And I suppose you could devise some kind of compression technology using principal components, but nobody really does it. But so, you know, what is it useful for us as, you know, people trying to analyze data? Well, it is often useful for data visualization, and it's also useful in terms of if you had to do some kind of clustering analysis or something of that nature. You might originally start off with very high dimensional data, and in order to, you know, just for exploratory data analysis, you may want to project your high dimensional data just down onto 2 dimensions or 3 dimensions maybe, okay? Because 2 dimensions you can plot on a screen, right? If you have 50 dimensions in your original data, it's like almost impossible to plot, okay? But if you have 2 dimensions, you can plot that down to 2 dimensions, and you might be able to look at that, and you might be able to see some structure within those 2 dimensions, okay? And those 2 dimensions, those 2 principal components, they are combinations of the original, you know, M50 dimensions that you have in your data, but they are kind of like the linear combinations of those things in such a way that you know, preserves the most amount of structure. Okay. Are there questions on this? Okay, well, maybe today we'll end a little bit early, and then if you guys have questions about homework and stuff, I can answer those. And, but we'll end.